Is there anybody else?
I will stay here until the end of everything, so if anything happens, I'll be right in there.
Okay, cool. Thanks. You're welcome.
Jane, email, burn.
Yeah, yes.
Email.
Thank you.
You're welcome. Right.
Now, I printed out all of my printer and all my others.
Oh, yeah. Why do you want a printer?
Yeah, maybe they like.
I just use the printer down.
How to use it?
You can connect it. You can connect it through the network.
Yeah.
There's like I think they have like documentation for it.
Oh, yeah.
Yeah.
But in my office, it's very convenient somehow.
I guess I don't print too many times.
Talking to the waffles you got there. Yeah. Oh, so sorry. This was the last one. You want to change it? No. The speaker took my snap. Now to talk with you. Good.
Yeah, yeah, it seems.
Yeah.
Finally, seems
Yeah.
person.
That's good. Okay. Cool. Very cool. So yeah, it's a great place. You want to go get ready for it? That was tough, right? Yeah. But the winter was not very cool. Like that. Like, it's not pregnant, but stone is. Right. Yeah, it's not, it's a lovely place. You know, I'm Canadian, but I remember lived in the US for about a year or oh, US. And I really enjoyed it. Oh, yeah. But, you know, a hockey game over there. There's a Cornell hockey.
Yeah,
Of course, I guess. You know?
Yeah.
Before every game, they play Canadian. I couldn't do American school.
Oh, I don't go there. I make it. I go to the energy and conservation conference.
I have in the same distance.
I think we usually do 4:30.
So what's your doing
Next year, we usually go to Zoom. Monday after.
I have, yeah, I want it.
Friday, we have the holiday party.
Yeah, that's useful.
I don't know.
Yeah, so.
This was me writing with this pen. It's like.
Okay. Maybe we'll slowly get started. We have a few people online on Zoom, and I think we have a reasonable number of attendees here. So it's my absolute pleasure to welcome David Sinton here as our seminar speaker. Thanks for making the trip from Toronto over here. And I think it's your first trip, so hopefully you enjoyed it so far. So David is a professor in the Department of Mechanical and Industrial Engineering at the University of Toronto, and he is a Canada Research Chair. His group works at a very nice, interesting interface of developing and understanding flow cells, for fluid systems with applications to electrocatalytic. And his group does a lot of interesting application-driven work for electrochemical systems, CO2 capture, water electrolysis, fuel cells, etc. A lot of interesting papers from his group, which I highly encourage you guys to checking out and reading. And thank you for making the trip, and it's been wonderful hosting you.
Well, thanks for having me. It's been a great.
is full, so I've got that to take on the plane back. So lots of great discussions. So thanks. I was going to say to all the PIs I got to meet today, but also grad students. We had fun over lunch. It was great to understand your experience here. I think you've got it pretty good. Very supportive department here. That's not all you've got. You're at Michigan, so I know that sport is important here. But the sport that's important in my family that they associate with Michigan isn't football, and it isn't basketball. Can anyone guess what it is? Hockey. And why do you think it's so special to my 10-year-old son, Michigan and hockey? Does anyone know why when I said I was going to Michigan, he was very excited? There's a goal called the Michigan goal, or the Michi. And it's a very special goal, and it was first done there was an Albany, a guy in Albany, New York, who started doing it at the lower level leagues, but it was first done in the NCAA and made famous by Michigan's Mike Legg. And how it works is this: you take your stick right down on the ice. Sorry, very stereotypical. You've got a Canadian here, he's talking hockey. Right? Stick right down on the ice, and then you twist it, but you have to have the puck right on the heel of the stick. So you twist it and then flip it up. So now you've got the puck on the stick like a platter, and then you can go around the net and just throw it in. It's a real trick shot, and it was first done in the majors or in the big leagues by this Michigan player. And as a result, it's called the Michigan, and it's famous in Canada. And the stick that he used, back in '96, is on display in Toronto downtown at the Hockey Hall of Fame. So lots of congratulations to Michael Legg. So that's the exciting thing for my visit here. In addition to CO2, which we're going to talk about. What would aliens assume? This is another Canadian story in a way. Václav Smil, some of you might know him. He's an energy economist, and he's Bill Gates' favorite author, which is saying something, because Bill's quite well read. And there's a joke that says Bill Gates waits for Václav Smil's next book, like people wait for the next iPhone. Like he just does excellent energy analysis, and it's not complicated, which is what makes it so potent. This example is inspired by his work recently. What would aliens assume? Aliens were approaching our planet, and they had a little chat going. They'd say, well, what have we got here? Well, they'd say, they know the size of the planet. They know how much radiation we get from the sun. And let's say they knew that humans were around about our size. They'd say, well, I'll tell you one thing. This planet's going to support 4 billion people, max. The occupation, what do? Rohini doesn't run a lab. She works most of the time growing food, right? That's what they do. They don't live in Ann Arbor. They live in regions that have enough sunlight to have significant amounts of growth in temperate regions. And then maybe the other alien would say, well, you're wrong. I've got intelligence that tells me there's actually 8 billion of these people here. And they've advanced service-based economies, and Rohini indeed runs a research group at a university, and there's all sorts of advanced knowledge-based work that goes on here. The other alien would wonder, well, how is this possible, right? And the answer is, we heat and we power and we move with the products of stored sunlight. We're cheating in a way, right? That first alien was right. We could support a maximum of 4 billion of us, even if all we did was agriculture. And we produce food with ammonia-based fertilizer. I'm inspired by some of the discussions we've had on nitrates and co-conversion with CO2. Ammonia-based fertilizer, and we build with advanced materials. And we do that, of course, because we've grown our energy supply over the last 200 years. And I love this chart because it shows, in some ways, it's what it doesn't show. We can see this is 200 years of energy history here. And initially there was biomass. When I used to present this, I made an error. I said, yeah, so we replace energy sources with better energy sources. But that's not actually true, right? We don't replace anything. We still burn exactly as much biomass as we did 200 years ago, or maybe a touch more. We tend to add. We add, we don't subtract. We find efficiencies. You can't see that in this plot. We've got engineers and many of the folks in this room can attest to this. We find a lot of efficiencies, but we don't, think about the changes over this century, right? 2 world wars, a depression, and more recently a pandemic. Honestly, didn't really change the needle much. A few little bumps. Okay, so that's what we do. That's the nature of our existence here on Earth. We grow in our energy appetite. I want to share one last story that speaks to rate. So this shows you a bit of history over 200 years. This little anecdote here in one slide talks about, for me, speaks to energy transition and speed. And this is Pit Hole, Pennsylvania, in the fall of 1865. So I'm going to tell the story of Pit Hole. All right. So Pit Hole was nothing but a forest in January 1865. And then someone struck oil in this forest. By June, Pit Hole had 4 flowing wells producing 2,000 barrels a day, which is 1/3 of the total output of the region. 2,000 barrels oil operation, that doesn't sound like a lot, but you got to remember, there was no vehicles, right? There's no cars. They're handling 2,000 barrels a day by horseback through muddy roads. There's no infrastructure, right? So that's pretty rapid scaling, January to June. By September, we're at 6,000 barrels per day, and the region supports 15,000 people, with hotels, banks, businesses, and a post office holding 5,000 letters per day. And you might be a bit confused here. This is 9 months since this place was a forest, right? Okay. November, oil production dries up, okay? By January, thousands have left town and fire ravages the buildings, and the town is reduced to 0. So when people tell you, oh, everything's fast paced today, life's fast paced, you say, baloney. Pit Hole, Pennsylvania, 1865. Start from a forest, grow a town of 15,000 people, burn it down in 12 months, right? That's speed. Now, listen, this is not necessarily what we want to do tomorrow in a new place in Pennsylvania, but the idea that we can move at speed when we need to, social services, industry, we can do it. We were doing this 200 years ago. We can do it now. Our own history, more humble than that of Pit Hole, Pennsylvania, and more recent in CO2 electrocatalysis. And this has really been a history in partnership with the Sargent Group now at Northwestern University, but they've been a big part of our story here. And really it was a partnership between what you'll see, the kind of stuff we do, a lot of emphasis on systems, on transport. I'm a mechanical engineer, and we focus a lot around electrodes and how to get reactants to those catalytic sites where we've got really nice catalysts, often made by Sargent Group friends, and how we get the products away, and how we get the electrons in from the side, and how we maintain the pH of the condition that makes it all productive, and how we do all that at current density. We're kind of, you can think of those mechanical engineers or chemical engineers equivalently as facilitating all of that transport system. So we moved from small products, like back in 2016, it's really all we knew how to do, small systems, small catalysts, and small products, right? CO2 to CO. And then we've really tried to grow that looking at larger scale products, so thinking about ethylene especially, and ethanol. And then some stories I'll tell along the way here about how we've changed our systems to address CO2 reactant utilization and efficiency. And then we got some scale work here that we started in the early 2020s, and then a more recent trip into CO2 capture. I'm going to start with the capture side because that's upstream, and I'll tell a few stories along the way here in our most recent work. And I'll do so with the framing of this figure here. We wrote this paper, CO2 electrolyzers. We hope it's useful to the field. It was a bit of an opportunity for us to, survey a lot of papers and try to assess, everything we've learned and everything others people have learned, or at least our best compilation of that in how to engineer CO2 electrolyzer systems. And we broadly think of these different pathways as where these electrolyzer systems can play a role. Incidentally, I never, I try to avoid people in my group writing chemical reviews. I try to wait till they're just about to leave my group, and then they're going into Rahimi's group, and then they can work, part-time. Doing that. That's partially true, but not entirely planned. But there are a lot of work. There's like 400 or 500 references in these things. Anyway, the key thing for today's purpose is we're going to look at different pathways here. We're going to walk through these ones. We're going to walk through these ones, and at the end, I'll share one about direct flue gas capture that we're proud of as well. But first of all, starting upstream on the capture side. So how to get from air, I know this is of interest to lots of folks here in Michigan, how to go from air into concentrated CO2 form that could go into any form of reactor. All right, well, the two leading, or at least most scaled systems that we know of are the carbon engineering and what we think of as the carbon engineering approach and the Climeworks approach. Of course, there's multiple players in these areas now, but these are famous touchstone ones. In the carbon engineering one, here they've got this calcium recovery loop. So I won't take you through all the details of this, but work pretty hard to get to a solid form of carbon, free that potassium back to the contactor, and as a result, it operates at 900 Celsius in order to get that CO2 out. Climeworks can operate at a lower temperature. It's got some other challenges. It's a bit more of a machine than a fluid process. And maybe it's from my mechanical fluidsy background. I'm kind of drawn to this. It's a chemical engineering process. Both have heat inputs. And the challenge with heat inputs is that you have to find that heat from somewhere. And especially in the case of carbon engineering, 900 Celsius heat, there's not too many places to find that heat. You tend to need to get that from fossil fuels if you need. So the result is you end up emitting significant amount of carbon per ton that you capture. So they can still come out ahead. It's still worth doing, but it just kind of hurts, doesn't it? It's like spending money. It's like paying a financial advisor. Like they help, but they cost. You know what I mean? So this is something we tried to address because we thought, well, if we can be powered by renewable electricity, we can reduce at least that. So this loop, and I apologize, this is a little bit complicated despite our best effort to color code this. But anyway, the core thing here is the electrolyzer and the acid base in and out. And as a result, this gets us in a separate CO2 liberator here. So you've got an air contactor, similar to, at least a similar principle to the one I showed in the last slide. And a CO2 liberator, this is just a pot where we're able to pull out the pure CO2. And then you've got the electrolyzer here in the middle that does alternating electrolysis. We saw examples of that earlier today. And this guy can get to much lower CO2 emissions per ton captured. And the other factor, the other number that we track in our work and others do, is the gigajoules per ton. So how much energy does it cost to do this? And we were looking at an example today. I think Rohini, maybe an hour ago, was showing me a nice example in work here of a fuel cell alternating mode in a capture type system. So this is a similar kind of operation mode here, a little bit of a different system. You've got a shared electrode here, and then you've got your fuel cell mode and your electrolyzer mode, and the key outputs are these acids and bases that are achieving your capture and your. So this was kind of Gen 1, and I apologize, I think I've got the wrong reference down there. This was a EES paper. This one, I'll get to the right reference in a second. But the last point on this one is that it was stable. So we were able to get 100 hours out of this. It's alternating, but we're able to get 100 hours out of it and more, we suspect. Okay. Our next effort was really inspired by a lot of the work done in organics and labs around the world. Increasingly, there's all sorts of nice studies on CO2 capture using organics, including here. And we thought, could we somehow use the strength of what we see, and apologies, mechanical engineer here, what I see is the strength of organic systems, this easy, rapid charge transfer that they can achieve, nice low gigajoules per ton numbers that they can achieve in principle. but avoid the Achilles heel. And the Achilles heel for these systems is, you know, carbon capture is inherently oxygen-y kind of job, right? Like there's a lot of oxygen, thankfully, for all the CO2. So exposing those organics to the oxygen exposes them to breakdown. So can we get the good part, the fast transfer, without getting the exposure of oxygen to our organics? So the approach was this one. We keep our organics kind of trapped. They're in that, you said they saw a CO2 liberator in the last slide. Oh no, I got the right references around here. Thank you. You get the CO2 liberator here, and then you've got a bit of a different process. You've still got lithium and you've still got protons being pumped across here. But in the middle, you've got these organics doing a nice charge transfer function. And then there's a bunch of work in this paper that my student Shiji and help from organic chemists really got. Essentially, this will look familiar to some folks that have experience in flow batteries. You want those carriers to be able to drop off and pick up electrons, right? And without being repelled, for instance, from one electrode or the other. And we found this one that seemed to achieve that. So this guy operated for over 200 hours and with 3.8 gigajoules per ton. So this is getting down there. I should have told you the limit. I think it's 1 or a little below 1 for the fundamental limit. So this is getting there. And it's applicable to DAC. So again, because we protected those organics, we can run with air and not have degradation. Great. So thinking about other steps. So when we've got pure CO2, what can we go on to? And we'll talk about this, what we'll call the direct route. So from pure CO2 into one-step electrolyzer. Our earliest work, this was now quite a while ago, well, I shouldn't say our earliest work, but one that I would say forced a change in how we operated was this one. We got to essentially using some tricks of the fuel cell trade, really great ionomer coatings of catalyst to kind of extend the triple phase boundary. I had a student, this was like a technological arbitrage, a fuel cell person came into our group and said, you guys got a spread electrode, here we go. And then that combined with some really great other folks, including lead author Paleo here, got really high current densities, right? So this is fuel cell tools essentially for C2 products. And that's just the guy here. So that was good. So I'm proud of this accomplishment, but you can see there's a but coming. This modeling here kind of shows the problem. You've got this really steep gradient, which means lots of transport of CO2 into solution. Why? This is an alkaline flow cell system. So this CO2 is eventually being captured, right? But this is not the capture part of the talk. That was 3 slides ago. This is the conversion part of the talk. And if my conversion system is capturing my CO2 again, that's really bad, right? This is doing a nice job of stretching and reacting along the surface. That's good, but this is painful loss. Okay, so we still get crazy high currents. That's good, but this really came to our attention with this really nice paper by Rabinovitz and Kanan, and a bit of a little pun here. The future of low temperature carbon dioxide electrolysis depends on solving one basic problem. What they were getting to there is the alkaline solutions here capturing the CO2. That loss of reactant is very expensive, and in this case, too expensive. So this really changed the course of my group's work for the years after, the 4 years since, because we realized we had to develop systems that were high single pass utilization. In other words, they didn't lose CO2 to carbonate. They didn't have this problem. So we've developed we're taking 3 different approaches to that. And I shouldn't say we're the only ones that the world has recognized this challenge. And there's been lots of great contributions in this area. They tend to fall within these. So bipolar strategies, acidic CO2 strategies. So working with acidic electrolytes. So so you don't get that capture of CO2 into the alkaline solution. And then cascade systems. I know Joshua and I were talking about these a bit. Okay, so we'll go through a couple examples of these. First on the bipolar guy. If you think about adding different membranes here, and this is a simplified schematic, if we just have a CEM, just A between our anode and our cathode, life is not that good. Because we end up with transporting all those protons through the cation exchange membrane here. It does what it does well. It take these protons over to our electrode, and then we produce too much hydrogen. We're always fighting the production of hydrogen when we're trying to convert CO2 to other carbon-based energy carriers. You can put a bipolar membrane there as well, and that does block protons getting all the way over. They don't get over to your cathode and do HER. That's good, but you know, where you form CO2 and H2O here, you end up with blistering and low stability. So you can actually see a membrane here. It forms this little bubble. It kind of blows itself apart. So we had two different early approaches to fix this. This one we called this permeable carbon regeneration layer. Essentially, it was kind of an AEM-like layer that was porous. And you see this a few times in the literature since then in different forms. But the general idea is you've got that, you don't form that blister anymore. You don't have this happening. You've got transport of that water and that CO2 back where it can react again. So this is a porous system that can work pretty well. And with this, you get, you know, 3 slides ago, I was showing that perspective paper that really said, hey, you guys are losing 99% of your CO2. You have to fix that. Now we're getting to use 85%. So this would be better if it was 100, but it was certainly a lot better than 1% or 2% or whatever we were getting. Okay. A second version of this, talking with a few friends here in Michigan today about different structuring ideas that we can do. And here's one example of using in the membranes where we structured channels in these membranes to kind of release that blistering pressure I mentioned earlier and bring that CO2 right back in here to a reactant, as a reactant. And this guy worked quite well. It's quite stable as well. And a bit of a hassle to make these microchannel membranes. Of course, it's just embossed. You know, you just squish it on there. But we do see some future for this. We've scaled this to 50 centimeters squared. I think the reviewers forced us to do that. It was a good ask because something so intricate, like how well can it scale? And to be honest, it worked pretty well. So I think we'll see. We haven't scaled this. We'll talk more about scale later in the talk. We haven't scaled this beyond that, but my sense is I don't know it's not going to work. Let me put it that way. And this guy's nice and stable, at least in the context of the field. We'll talk a little bit about stability later. This is the norm in the field for a good paper. 100 is also considered kind of acceptable. Of course, the actual goal for the field, does anyone have a guess? What do you think? Or have an opinion? What would be, if we were going to the field tomorrow, going to start a company and sell electrolyzers, what kind of lifetime are we going to need in hours? What would industry expect? What's that?
10 years.
10 years, they might want 10 years. You know, but at least something like, yeah.
10,000 hours.
Something like that. Yeah, it's going to be in the same realm that electrolyzers are, right? So we talked about technological arbitrage, stealing things from different areas, applying them. If we think about the experience of electrolyzers, yeah, you're in the right ballpark. So not 200, but much further. But this is sort of the state of where we're at now. Great. An example of acidic systems. So here, the acid idea is, you know, kind of a good one, right? You work with acidic electrolyte, and you don't have this alkaline electrolyte stealing your CO2 away, but you've got some other problems, right? We had a first paper. I'm not going to show that here, but we just really turned up the cation concentration. We worked at really high cell concentrations. We worked at really high currents. In that case, we worked at really high currents, not because we wanted to work at high currents. We worked at really high currents so we could get a locally alkaline condition at our anode. We basically worked our way to a locally alkaline condition. This version is a little more reasonable current density, and this was a strategy by my postdoc, Meng Yang Fan. And hers was, alkaline cations and acidic CO2R form salts, and it's bad news. If we put an ionomer there with cationic groups, we can use less cations. So we call this a fixed cation strategy. And then a carbon layer helps protect the cationic group and keep the thing stable. So we were able to get a record stability for acidic conditions to 150 hours. And the mix of and 90% carbon efficiency. So again, that CO2 utilization efficiency was getting up there. And the mix is reasonable ethylene and ethanol production here, and still some residual hydrogen. Great, so that was the direct route we just talked about. Here's some examples of that guy. And then now the tandem route. So again, from pure CO2 through a two-step. And you might be wondering, why would you go through a two-step if you can just go through a one-step? Certainly, that's a valid concern. We'll talk about why this two-step has some advantages we think are compelling. It's one we call the cascade approach. And here we use the solid oxide system, which, especially when we started in this field, was really, we thought they were perfect. Solid oxide systems can convert CO2 to CO very efficiently, very low gigajoules per ton, and they don't have that carbonate problem. So it's pretty attractive, and you just order on Amazon or whatever. Like it's a very developed technology. So we thought, oh, that was great. Then we can, if we get CO from this thing, then we can just build this thing. And that was kind of the idea. Use the solid oxide cell, let it do what it does well. Nice low voltage. Look at this, 1 volt kind of thing, and then focus on the MEA, which would be our intellectual contribution. So this is a cascade, one established step and one MEA. I think now I do worry a bit more about the solid oxide step. I do cheer them on, but I think there's some concern there as to how the extent to which these will scale. I certainly hope they do. Our step here, carbon monoxide electrolyzers, we've done lots of work in this area. I'm going to show an example or two here. One nice thing about this process, the overall process can be 50% of the energy cost of the direct route. So it really gets to a rough rule is CO2 reduction. Good ones are around 3 volts, or maybe around 3 or 3 something. Good COR is around 2 or 2 something. And that matters because the number one cost of an electrolyzer person is electricity cost. We have a industrial partner that says, you got to work on 3 things: voltage, voltage, voltage. Because that, it hurts a lot. The electricity cost hurts a lot. So voltage means a lot. Having the opportunity to work at 2 volts or close to it means a lot. So that's why we're so drawn to this COR. So, generally combined carbon energy efficiency is a challenge in these things. You can see here, you can get energy efficiencies up here towards the right at higher CO flow rates, but your single pass goes down. This is familiar to all the chemical engineers in the audience. And then, of course, you need to have both energy efficiency and single pass conversion to be profitable. So here we looked at another approach of controlling that interface. In this case, with really controlling the cation concentration at surface. We called it engineering the Helmholtz plane. So this worked pretty well, and we could get to essentially low resistance and good kinetics. And the way we achieved that was with a cough from a collaborator. But the key mechanism is all about what we achieve at this interface. This concentration of hydroxide. So again, a locally alkaline condition. It's very favorable for CO conversion, and not have them butted out too much by by cations. And this guy was stable 200 hours, and you can see in that plot where we wanted to get up in the yellow zone, we're getting up close, up into the energy efficiencies that are getting respectable, 50%, 40% overall energy efficiency. And then single pass conversions that, depending on which one you pick here, are getting high-ish. So working our way up and to the right into a practical technology. All right, so where have we been? We've been here, we've been here, we've been one trip through here. So I want to take you on one trip direct from here all the way through here. And the vision for this is, if we can react flue gas from point sources directly, then we can skip the separation steps, we can skip the capture. Point source capture is much more established than direct air capture that we talked about earlier. Thermodynamically, it's an easier job. There's a lot more CO2 here available. There's still some challenges with this, and it's kind of a grumpy business. So using direct flue gas, especially if you're converting it anyway, it's nice to be able to skip that scrubbing and separation step, go direct, if you can. And the answer before our work was largely that you can't. There's lots of motivation to do so. Point sources make up a great deal of the emissions that we produce. I mean, some are certainly not what we would call point sources, right? Like transport emissions. The plane that I took to get here was a very diffuse source. We're not gonna. If you want to get those carbon dioxide molecules back, we got to do air capture. But some of the power generation, other industrial sources, industrial processes, fuel production, certainly, a lot of those sources are coming up through smokestacks that have relatively high concentrations. And here's what we call our flue gas menu. We've got natural gas plants, coal-fired plants, cement manufacturing, steel manufacturing. And you've got your CO2 concentrations and then your other bits, right? And one thing that's been a lesson for me as a mechanical engineer, kind of trying to pretend I'm a chemical engineer sometimes. By the way, I fooled them at University of Toronto. I'm a status-only member of chemical engineering there now. This isn't being recorded, is it? But I learned that, I used to think, well, it's all about this. That's all about this. Get the more CO2, the better on the menu. But the chemical engineers I talked to said, whoa, wait, I want to hear about the PPM stuff. I was like, why do you care about the PPM stuff? Like, look at this. Like, well, because all of our costs are going to be driven by the PPM stuff. So it's the nasties, right? And the nastiest of the nasty is this one. At least for catalysis, the nastiest of the nasties is that one. These are the sources we tend to gravitate towards. Why not this one so much? It's still a big source. It's because our solution is electrified, right? We take electrical energy. So if your electrical energy input is coming from a coal-fired plant, you're not producing a lot of benefit. Our technologies rely on low carbon electrons. That's what makes them make sense. Okay, but these sources are likely to be persistent, and they're pretty high ppm in SOx. And then the other thing I'll add about SOx is some people say, well, why don't you just scrub it? It's a pretty easy process to scrub it down. Yeah, existing scrubbers do scrub down, but they scrub down 10x or 100x, but not to 0. And catalysts are super sensitive to sulfur. So I would argue streams from here, we're going to have to deal with sulfur, whether you're post-scrubber or whatever. It's still there. Okay, to what extent does it cause a problem? Fengjiao has some nice work in this area. Ours shows similar trends here. A little bit of SOx poisons the copper rapidly and irreversibly, right? So here you can see adding the 100 ppm, things were, kind of okay here. We had some sort of typical blend of C2 plus and some CO and some formate and some hydrogen. Add the SOx and all of a sudden, all of our products, desired products, carbon-based products shrink. And this is, a poisoning mechanism that's been seen by others And we certainly see that tends to go towards formate and hydrogen. And we can see this for, different concentrations here. If we have even 10 ppm after 2 hours, we've got a pretty substantial reduction. And after 100, and with 100 ppm, it's faster. And with 400 ppm, it's more so. But either way, the message is if you've got a little bit of SOx in your stream, your catalyst is going to be irreversibly damaged. So we thought, how can we somehow slow the transport of the SOx and preferentially allow the CO2? And initially this really stumped us because chemically these don't look that different, right? SO2, CO2. But the secret, and there was a few layers to this paper, and if you're interested in all the details, of course, are here. But the overall gist of it is combination of hydrophobicity, so keeping water away. We found local availability of protons to be really important, and slowing the SOx by having interactions with the backbone of the PFSA here, and a combination of PFSA and PTFE. Yeah, and sorry, I should have clicked here. We really saw the importance of wetting and the influence of sulfur on our copper surface. So this really gave a clue to two roles there. One is wetting water at the catalyst, comes up all the time. It's super important, and it's important here in this mechanism, and it's important in poisoning. And then two, trying to slow that SOx down. So with this guy, I don't know if I have a pretty picture of this guy, but it's essentially a version of that, but built up in sort of a multi, a sprayed catalyst with lots of reactive area. Got to pretty decent performance here. This is in the case of just SOx at 400 ppm straight out of the smokestack. We're able to go cruise for 100 hours. So no longer death after a few minutes, instant death, but rather really continued production over 100 hours. And as I mentioned, the field is not really that much beyond 100 hours reacting pure CO2. And this is a pretty nasty stream. Also, full flue gas here. So SOx, add some NO, add oxygen, and we get reasonably productive flow here. We tested this over 8 hours. So there's some indication that this could be applicable to a full flue gas mixture, no separation, direct into your electrolyzer. Great. So with a few minutes remaining, I want to talk about, maybe this is just because I'm turning 50 this year, but I'm conscious that we've made good progress in the field, but two things haunt me, and one is scale, right? Ultimately, we work in labs, a lot like your labs here. Mine are dirtier, by the way. But they're not huge systems. They're not, we think of carbon, any carbon tech needs to be absolutely massive. Mine aren't that massive in my standard labs. So we looked at, can we scale our work, and to what extent can an academic lab sort of reach out to meet industry somewhere in between the scales that we typically work at and what they must achieve. So small, and then slow also. I know I'm very proud of our progress, but it takes years to do this stuff, right? So there are ways to accelerate. So first on small. We've got a scaling facility now. This really came out of, we use war terminology here, fighting the X Prize. X Prize, this was not the current carbon X Prize, but what they called it was called Carbon X Prize, Nicosia Carbon X Prize. The current one is called the Capture X Prize. This one was a conversion effort, and it was led by my postdoc, Christina Gabardo, who now leads certain systems, Inc., which is a startup out of Toronto. And that process, a couple things came out of that process. Spoiler alert, we did not win the X Prize. A process like CO2 to ethylene electrocatalytically, you can kind of get a sense for looking at this, pretty complicated. You're probably not going to win. But you're going to have an opportunity to scale at a rate you wouldn't be otherwise, right? Like if you folks here said to your funders, hey, I want to scale 1,000 times. It's lab bench thing. I want to scale 1,000 times. Your funders are probably going to say, here's some money. How about 10 times, right? Why don't you try 10 times? It's a sensible kind of response. So scaling something 10,000 times is not sensible, but you learn a lot when you really jump scales. So this was an opportunity to build a team, and we had a deadline, we had the prize, we could raise some money. So we did all those things, and I'm really happy, glad we did it. And now this thing is home. There's an engines lab at U of T with some old, beautiful steam air compressors and stuff. They've got a corner of it for me. It's an industrial space, really. And we have this multi-bay electrolyzer. So these are power supplies here, and then the cells sit on top, and then this is all just fluids, and this is all controls. So this guy is alive and ready to scale as a scaling facility. One example of a study that came out of that work and is now just published by my PhD student and now someone who's at the company I mentioned. His name's Colin O'Brien. They had trouble. They bought, of course, commercial carbon papers to fit in this giant electrolyzer system, and they were getting flooding at 30 hours. And that's not such a bad deal if you just got a little system in the lab, you're doing your paper. But if you just put a whole plant together and you spent, I don't know, $50,000 in membranes, and you took a week to assemble all the cells, and the thing lasts 30 hours, that's a really bad day, right? So that's just how scale and stability, which I've mentioned a few times, have to grow together. Because there's just no point in scaling something that's not stable. So he needed more. So he was sort of forced to innovate here. What was happening in these commercial carbon papers? He was getting lots of salt buildup, lots of potassium salt buildup down into his microporous layer. And then, of course, salt crystals forming, and then folks here who know the field will know what happens here. This reduces wetting and then causes flooding. This complex dynamic there, it's worthy of study, but it's pretty clear that that's what was happening. Okay, so he developed this, what he called a segregated MPL, and don't forget, his goal is not to write a paper. His goal is to build the world's largest CO2 electrolyzer. So he's doing this on large sheets. So he's doing this through, doctor blading mixtures of materials that he can get at large scale. So here he's got this, what he calls a segregated MPL. And with that, he can get to, a couple hundred hours, 500 hours in this case, or 400 hours. So a 10-fold increase in stability, which really made it possible for them to scale again. And then we had some friends that helped us understand the structure here of what Colin had created. And he's got the porous carbon is connected, so he still gets the connectivity, so it's electroconnectivity. And then there's the PTFE layer. So that's where he gets this sort of segregated MPL concept. And this guy, as I mentioned, worked pretty well. If you compare 800 centimeters squared cells, that's our largest cell. Why 800? Why not 1,000? When we started this, we could only get membranes that were 20 centimeters wide. So, by the way, you might say, "Oh, I'm building my electrolyzer this way." No, you aren't. You're building it this way because that's all the material you can get. So 20 by 40 kind of made sense. Right, so the 800 centimeters, now a single cell, we got this to run a couple hundred hours, and then same for the 8,000 centimeter squared stack. So that's one, you can picture that's one bay of that big electrolyzer pilot plant. Again, running for a couple hundred hours. And I think this is one of the bigger, or perhaps the biggest demonstration of, or when this whole plant was running on this, I should say, with the 5 electrolyzers, was a big operation in the context of CO2 conversion, but of course, small in the context of our collective goals for this field. Okay, I was going to mention, how can we accelerate? How can we go a little faster? You think about, one student, one cell in the lab taking grabs of their gas to the GC, that's kind of the current mode that's familiar to folks here as well. We developed this system as just kind of a 10x version of that. And this has been surprisingly useful. And in some ways, when we did it, I thought, well, this isn't going to blow anyone's mind. It's just 10 times the same thing. But you know what? Standardization helps a lot. And when you're doing something 10 times, you're getting better data than you would with an individual cell. And somebody takes a little more, someone takes a little less, someone has a lot of coffee. You know, there's sort of, we have a standard procedure for these. So I often think we talk about high throughput, but maybe a lot of the benefits come from standardization as a result of that. So this has outweighed our expectations, and also in terms of interest from industry. This work is funded by Meta, and Meta wants that data for their Open Catalyst platform. There's a cool paper that they've got up on Archive as of last week that has this, and they're predicting their predictions in it. And again, what's a company that's after the data interested in? They're interested in reproducible, good quality results, right? And then the system was able to give that. It keeps running. Where to next? Really, it's really closing the full loop on that, right? So predicting, using AI to predict a great material, then down selecting, by the way, those 100 materials you recommend, only one of them is synthesizable, then going and finding a way to synthesize that using high throughput. We use a ChemSpeed robot often, or a VS particle system, right through device testing. That's sort of our forte, and then results with AI, and then back around to the beginning. So that's the vision, and I hope we get there. Those other folks had some good discussions here, also very active in self-driving electrolyte processes and other things. Great. With that, I'd like to thank the folks that do all the work. This is my group here, and funders as well. And most importantly, thanks to you for your attention and a great visit today.
A few questions. Neil?
Hey, we got great talk. So many different things I'd like to ask, but I want to zoom in on the sulfur and the flue gas. Right. So if I understood correctly, you have this sort of polymer that prevents the sulfur from reaching the copper catalyst. Is that right?
Right, and it's doing two things there. It just slows it relative to CO2. And there's what we understand there's two mechanisms. One is it's the hydrophilic portion, where we've got the SO2, and the SO2, there's a lot of sulfonate groups in that PFSA, of course. So those interactions slow the effective diffusion of that sulfur through the system. So that's one. And then the hydrophobic backbone that allows the CO2 to pass. It's not fussed by the sulfonic groups. I think that's a key part of it. And then the other part of the success, I didn't go through all the steps, but we did see substantial benefit just from reducing the wetness of the catalyst. So the local availability of water or protons at the surface, that was important in stopping the poisoning as well.
So I guess my simple question is, so you don't poison the copper with the sulfur, but are you essentially poisoning the polymer? Like,
yeah,
is it accumulating sulfur and you have to sort of throw it out?
Yeah, it's a good question. I don't know. We didn't see it break down on the hundreds of hours that we ran for. It wasn't obvious that was a, does it
So is it
fill
like a
up
shield
or?
for sulfur, or is it like a getter for sulfur?
That's a good question. I want to say shield, but do I have proof of that? I think the only proof one could have is just the long term that it did seem to maintain that function. I'm guessing the best, I'm picturing sort of a response to reviewers here, is to calculate how much,
Or did you do like a T?
Right, how much the SOx could be possibly stored in that layer, and then how much SOx washed by. And if it was 1%, then we'd say, no, it's a shielding effect and it's permanent, as opposed to, no, we just cut the first couple hundred hours worth of sulfur and we were good. That's a good question.
I have, thank you for great talk. So basically, I have one general question. I'm from different backgrounds, so just curious to know. So which process, like whether it's photocatalytic or electrochemical process, is industrially relevant. And I see that electrochemical takes a lot of energy and it's very complex process.
Right.
In that case, to me, like photocatalytic process can be very efficient. But what is your opinion that which
Right.
processes can be better?
Ours is the best. I think, I saw lots of nice photocatalytic approaches here, and I think maybe one of the nice things I think about what I'll call the U-Michigan approach is a bit of ambivalence, right? Like we're trying lots of different routes and as we assess, not unlike what we do in electrocatalysis, trying to keep routes alive until we're pretty sure they're outcompeted. In our case, I did start out doing photocatalysis way back when, and we transitioned to electrocatalysis, and maybe part of that is because of the reactor design side. Like, let's say if I went back to Toronto and I said I was really inspired, guys, at University of Michigan, not just because of the hockey heritage there, but because, the photocatalysis work, I want you guys to start getting light inside your reactors. Like, they're gonna look at me like, honestly, Dave, you ask, like, that's just a bridge too far. Like, we are not, like, it's hard enough to do this stuff, right? You gotta get reactants there, you gotta get products away. Like, now you're gonna get light in, like electrons are just fundamentally easy to guide. You didn't hear me talk much about electrical conductivities. It's not like you gotta pay attention to it. And as you scale, it's a bit of a little bit of challenge, you get a thicker layer or something, but it's not that hard. But getting light in things is hard.
Okay, good.
So that's why we went away from it, but the debate's not over. This is not settled. You just sort of, as a researcher, and you will in your own career, you kind of place your bets, right? And you can see we've placed you place a few bets, but you can't place all the bets. So you can sort of see where we're at right now. But that'll change.
Good. Thank you.
Great.
So I'm interested in this like carbon paper and the flooding problem to solve. And obviously these carbon papers are, we're just kind of grabbing them off the shelf. We're not making them specifically for this purpose. So I was wondering what kind of optimization you see that the carbon paper morphology could undergo in the future, and what kind of commercialized techniques could be used to kind of optimize morphology.
Yeah, it's a good question. I think there is a lot we can do, and particularly on carbon paper, right? One example is sort of buy it, right, as the best you can get or the most relevant you can get. Of course, they thought they were making it for a fuel cell or for electrolyzers, but you're using it for CO2, and then modify it, like Dr. Blade it with layers, like I had there. That can get you somewhere. Custom ones for CO2, I think they'll come. To be honest, I would like those, but I would also like membranes that were designed for us and for our conditions, especially better AEMs. We have some darn good ones. There's a Canadian company, Ionomer, and we wouldn't have gone nearly as far in the X Prize if it wasn't for them. Keep going, right? Even better ones. We need those that last, and it's not just our technology, it needs those AEMs in general. They need to be better if you want to get to that 10,000 hours. So all the way through there, and then also in how these components go together, I find it a little hard to believe that buying these things off the shelf and then putting them together and tightening with bolts is somehow optimum, right? Like, it doesn't make a lot of sense. You're probably, all those interfaces could be better. They could be glued together or blended. We've experimented a little bit, but I don't think enough with direct membrane deposition, so spraying yourself, different layers, blending properties. We've showed a lot of BPMs there, blending properties of different materials, right from the binder through to the first membrane. And there's a lot of this, it's really an open design space there. So I guess the lack of available materials for us is a bit of an opportunity for researchers, maybe startups too.
Yeah, thank you for that wonderful talk. Of the variety of topics that you covered, I really want to zoom in on this last topic that you mentioned about the scalability. And I think it's so important, I think, that you highlighted that, because so much of catalysis is so relevant to being scaled up.
Right, or is it relevant if you don't?
Exactly.
Yeah.
So my question is, for all the different, research that we're doing at the University of Michigan or other researchers, what is your insight or advice for making sure to set the appropriate constraints or maybe the perspective in order to make the research that you're doing something
Right.
that can be industrially relevant?
I think it's a great question. It's something I wanna, it's something I wanna write on. Actually, I'm really motivated to think more about that. But I'll share what I'm thinking right now. A couple things, constraints, right? We chatted a little bit like that about that with the group over lunch. I think we need to rule out some catalyst preparation methods, for instance, that don't currently have a route to scale. And by the way, when someone figures it out and gets route, then we'll bring it back. But it's not a moral stance, right? But an example like sputtering, I don't think there's a route to scale for a sputtered catalyst. So I don't ban sputtering in my group yet. But people that are on the scale track, we say, hey, what's unique about your project is you're not allowed to do that, right? And that's part of your story. It's part of the narrative of your paper. How do you get to performance without that? Sprayed catalysts, sprayed particle catalysts, that's the only route I know to get to scale. We have a chart in our group. It's called the 10,000 Hour Club, and stability and scale kind of go together. And you look at how are those made, right? And it's sprayed catalysts, a lot of naphthalene, a lot of platinum. You can sort of look, that's the menu of stuff that's been there to 10,000 hours. So using some of those rules, sort of say, so it's sort of looking at your workflow and saying, if I'm really focusing on the scale is if that's my discipline here in this work that I'm working on, then which of my materials or processes is not scalable? And if you find one that is not scalable or known to be not scalable, take it. And then the good news is that's part of your story, right? That you can't, that's part of the innovation, is you figure out how to get around that process that's not going to scale.
One more question. I have a question on, you mentioned anion exchange membranes.
Right.
And you also mentioned that they are quickly getting very good. And I know that,
Let's say better, yeah.
yeah, so I guess are they on path to becoming as cost competitive with anion exchange membranes?
Cost, I don't know.
Mhm.
I guess, there's probably folks in the room here that know the materials involved. I don't think there's any iridium in that there's no fundamental reason why the cost couldn't come down. So let's give that industry the benefit of the doubt on cost. On stability, on the 10,000 hour thing, we have to see. Yeah, that would be the bigger one. But let's say cost, we think they could probably get there, at least to naphthalene levels, which is not zero either. I know it's a significant cost too, but at least it's not scale blocking. Yeah. Yeah, I think there's lots of work to be done there as well. And then also, we challenge the team to really think about alternative geometries, think about really wacky reactors and question assumptions and shop the full catalog, do the full technological arbitrage. Any other, I don't know, you can use AI to do this now, right? Like what has Perplexity or ChatGPT, what are the top materials that have been used in water electrolyzers and fuel cells for the past 30 years? Which ones have been most stable? Which ones get best ion connectivity? Just shop the whole catalog, all of it. There's been thousands of PhDs that have come before you. Might as well use their stuff.
Okay. No more questions. It's thanks to you. Everyone.
I'm gonna run to pick up my kids, but wonderful discussion.
Yeah, thanks for
the discussion. One question for you, somebody who's gonna be from the field, I'm gonna go read all these papers. Maybe you want to share like the opinion. I don't know that I can do all